When people first encounter modern artificial intelligence systems, especially large neural models, one of the most confusing aspects is how we decide whether a model is actually good. Training loss tells us something, but it is rarely sufficient. Real progress in AI has always depended on standardized evaluation, shared datasets, shared tasks, and public leaderboards that allow researchers to compare systems under the same conditions. Understanding benchmark datasets and leaderboards is therefore essential to understanding how AI research advances, how claims of improvement are validated, and where the field can sometimes mislead itself. At a high level, a benchmark dataset is a curated collection of examples designed to test a specific capability of an AI system. The dataset defines the task, the input format, the expected output, and the evaluation metric. A leaderboard is the public scoreboard that records how different models perform on that benchmark under standardized rules. Together they create a competitive but structured environment that encourages measurable progress. For a technically minded audience, it is helpful to think of benchmarks as the experimental apparatus of machine learning. In physics, you might measure the strength of a material under controlled stress. In AI, you measure the performance of a model under controlled data conditions. Without that shared measurement infrastructure, progress becomes anecdotal and difficult to verify. To appreciate why benchmarks matter so much, consider the alternative. Suppose every research group evaluated their models on different datasets, with different pre-processing pipelines, and different metrics. One group reports 92% accuracy, another reports 88%, but the tasks are not identical. There would be no meaningful way to compare systems. Benchmarks solve this coordination problem by creating a common reference point. However, benchmarks are not neutral objects. They encode assumptions about what intelligence means, what tasks matter, and what constitutes success. A technically sophisticated understanding requires recognizing both their power and their limitations. Let us start with the anatomy of a benchmark dataset. Most benchmarks have several key components. There is the task definition, which specifies what the model is supposed to do. There is the dataset itself, typically divided into training, validation, and test splits. There is the evaluation metric, which converts model outputs into a scalar score. And finally, there are rules governing how the benchmark should be used, such as whether external data is allowed. The task definition is deceptively important. Small changes in task framing can dramatically alter difficulty. For example, a classification task with balanced classes is very different from one with heavy class imbalance. A language understanding task that allows multiple correct answers differs fundamentally from one requiring exact string match. Good benchmarks attempt to make the task well specified and reproducible, but ambiguity often remains. Dataset construction is another deeply technical process. Ideally, benchmark data should be representative of the real-world distribution the model will face. In practice, this is extremely hard. Data collection pipelines introduce sampling bias, annotation artifacts, and hidden correlations. Models frequently exploit these shortcuts rather than learning the intended capability. This phenomenon is sometimes called benchmark gaming or dataset overfitting. For a highly technical audience, it is worth emphasizing that benchmark datasets are themselves statistical objects. They have distributions, noise properties, and annotation error rates. If the test set is small, the variance of the reported metric may be high. If labels are noisy, the benchmark may impose an upper bound on achievable performance. Many leaderboard differences that appear meaningful are actually within statistical noise margins. The split between training, validation, and test sets deserves careful attention. The training set is used to fit model parameters. The validation set is used for hyperparameter tuning and model selection. The test set is supposed to represent unseen data used only for final evaluation. In a well-run benchmark, the test labels are hidden to prevent overfitting through repeated submissions. However, over time, even hidden test sets can become indirectly overfit. When many researchers repeatedly tune models against the same benchmark, information about the test distribution leaks through the validation process and the leaderboard itself. This is sometimes called leaderboard overfitting. It is one of the central failure modes of long-lived benchmarks. The evaluation metric is another critical design choice. Metrics translate model behavior into numbers, but every metric emphasizes certain error types over others. Accuracy treats all mistakes equally. F1 score balances precision and recall. Log likelihood captures probabilistic calibration. GLUE and Rouge focus on surface similarity and text generation. Each metric encodes a value judgment about what matters. For language models in particular, perplexity has historically been the dominant intrinsic metric. Perplexity measures how well a model predicts the next token in a sequence. Mathematically, it is the exponential of the average negative log likelihood. Lower perplexity indicates better predictive performance. But perplexity does not always correlate with human judgments of quality, especially for tasks requiring reasoning or factual correctness. This gap between intrinsic and extrinsic evaluation is a recurring theme in AI benchmarking. Leaderboards sit on top of these datasets and metrics. A typical leaderboard records model names, scores, sometimes parameter counts, and occasionally compute budgets. At first glance, leaderboards appear to provide an objective ranking of systems. In reality, interpreting them requires caution. One subtle issue is comparability. Two models on the same leaderboard may differ in training data, compute budget, parameter count, or fine-tuning strategy. Without normalization, higher scores may simply reflect more compute or more data rather than better algorithms. For technically sophisticated evaluation, researchers increasingly track scaling laws and efficiency metrics alongside raw performance. Another important aspect is statistical significance. Leaderboards often report differences to multiple decimal places, but the underlying uncertainty may be large. Suppose the test set contains only a few thousand examples. A difference of 0.2% accuracy may not be statistically meaningful. Proper evaluation ideally includes confidence intervals or bootstrap estimates, but many leaderboards still present point estimates only. The culture around leaderboards has profoundly shaped modern AI research. On the positive side, leaderboards create clear goals, enable reproducibility, and accelerate incremental progress. They allow small research groups to demonstrate improvements in a transparent way. They also help industry practitioners choose models based on standardized comparisons. On the negative side, leaderboards can encourage narrow optimization. When researchers focus heavily on a single benchmark score, models may become specialized to that dataset rather than generally capable. This phenomenon is sometimes described as teaching to the test. Over time, benchmark saturation occurs, scores approach a ceiling, but real-world performance may still lag. To understand how this plays out in practice, consider the life cycle of a typical benchmark. Initially, a new dataset is released and baseline models perform modestly. The task appears challenging. Researchers begin experimenting with architectures, training tricks, and data augmentation. Performance steadily improves. Eventually, progress slows as models approach the benchmark ceiling. At that point, the benchmark may no longer discriminate meaningfully between strong systems. This saturation process has happened repeatedly across computer vision, speech recognition, and natural language processing. When a benchmark saturates, the community typically responds in one of several ways. Sometimes the dataset is expanded or made more difficult. Sometimes new benchmarks are introduced that target more complex capabilities. Sometimes evaluation shifts from narrow tasks to broader, multitask suites. For a technically advanced audience, it is important to recognize that benchmark design is itself an evolving research problem.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.